Okay, so what we want to look at is the fixed boundary of a cat0 metric space. So we have already defined what is a visual boundary of a local cat0 metric space, which is given by the as I said, they are both the same asymptotic equivalence classes of geodesic. Geodesic rays in that cat0 metric space, but we want to give it a new topology, which is the text metric topology, and which will give us more information about how the metric space behaves in large scale, at infinity, to be precise, not just large scale. Right now, to motivate the construction, I have to motivate what is called the length space, length metric of a given metric. So I want to motivate that first. How do you talk about it? So consider the unit sphere in Rn. Yeah. For n equals to j, it's a unit sphere in R3, and now consider there are two metrics. So there are two metrics on the sphere. First one is coming from Rn. So you have like the Euclidean norm, the L2 norm gives you a distance function in Rn, which induces a metric on Si-1 as every subset of a metric space is a metric space. So this is Rn, and then I can look at the inclusion map, and then push forward. This should be the push forward. Yeah. No, it's not the push forward, it's the pull back. So it should be this. Now, this is not a good metric on Sn-1. So this is the chordal metric. It will be, if these are x and y, the distance would be this chord length of this chord x minus y. Now, there is another metric on Sn-1 which is more intrinsic. It has much nicer properties, which is what you do is so you have the Riemann metric on Rn, you pull it back, and that is what is called the Riemann metric on Sn-1, and then this induces this Rn, and this induces this B of Sn-1, which are not the same. So this pulls back to and these two are not the same. This one measures, this is the arc length distance. So this one measures this arc length, so the length of this great arcs between 2 points. A way of expressing what they are is this is precisely x dot y. This is the dot product. The unit vector is this dot product gives you a number. Cos of this one. Cos inverse of x dot y is obviously not the same as x minus y. So this just x values in y. The diameter of the unit sphere is pi, and this takes values in 0 to 1, something like that. 0 to 1, 0 to 2. No, it will take values in 0 to 2. The maximum distance will be the diameter. This one, chord length. Will take values from there. Yeah, this. Yeah. So, how do you construct the intrinsic? This is the intrinsic metric, and this is the induced metric. How do you construct this from that? I know how to construct using a Riemannian geometry. I want to construct just in the metrics because the asymmetries, geodesics are all distance properties, distant metric properties. We can describe them and we can compute them using just the metric. I want to know how do you get this intrinsic metric of Sn minus 1 from Rn. And there is a nice intrinsic construction of these which is nice to look at very generality. Yeah, it's at a high generality. So what you do is you look at metric spaces. What we want to say is this d Sn minus 1 of xy is actually the length of the length of the curve is the minimal length. So infimum of length of curves. But what is this? So this is length of curve using the intrinsic metric. To do this, we need to somehow compute length of curves in a metric space, which is shocking. We know how to compute length of curves in a Riemannian manifold. Just take the velocity, take length of smooth curves, take its velocity, and then take its norm, and then integrate. How do you do that with continuous curves? This is just a continuous map. Well, given it's from opens. From a metric space, it behaves nicely, but how do you do this? How do you define this length? You do this in the following way. Call this x actually. Curve just means it's continuous. Now we want to define its length. What we can do is, this is some length. We can divide it into pieces. This is C of A. This is C of B. We can divide it into pieces and then take the distance, take this distance, take this distance, this, and then sum all of them. So we need to take a partition of so I have to take partitions. So now I have to take all partitions. So you take a partition of AB. They are numbers from A, T1, some Tn, B. This is increasing tuple, and you sum all of these distances, and you have the number of partitions minus 1 many. And how do you say, what do you do with this set? You have this partial sums. How do you say, I want to pick the best approximate, I want to take the limit of, in some sense. How do you do that? So what you have to observe is, if I take a finer partition, I partition it in further smaller pieces, and I take the length. Then this sum will only increase, because this, by triangle inequality, this sum is larger than this sum, other than equal to. So this will only increase, it will never decrease. And any two partition, I can take a common finer partition by taking the intersections. So what you do is you take a supremum. And this would be a number in 0 to infinity. Because supremum always exists in 0 to infinity. And that is called the length. The length of C. Now, if length is finite, then C is called rectifiable. Usual terminology, yes. Yeah, so we can compute length of curves in a metric space, which is shocking. Yeah, I mean, this is something we can do. So this is mimicking Riemann integrals, but we don't have to do the integral. We can do this in Rn, and we don't have to do differential geometry. We can just do metric geometry and then define length of curves, define curvature less than equal to 0, less than equal to kappa, and we can work with these rather than doing differential geometry. Right. Now, a metric space is called a length space. If this thing a metric space is called the length space if the distance between 2 points is the minimal length. This would be d. Lengths, we have already defined it. Length occurs in the metric space as d. If this is equality. So this might not be true. This is not true for the induced metric on the sphere, unit sphere, because the length of this curve is the infimum one, the smallest one, which is that, how do you know it's smaller? Oh, okay. So this is of course smaller, this is larger. But the thing is, every curve, this is the smallest length a curve can have. The distance between 2 points is even smaller. So that is why the distance can never be equal to this. Yeah, so this number is actually not. This is a number. Which can't be 0. Can't be. This is a number that is between d of a. There's a lower bound. C of b. Because I'm taking supremum, and this number is here. This of course is the greater than that. C of b. Yeah, there is a lower bound. So when the length is precisely equal, the infimum of length is precisely equal, then we say it's length metric. Yeah. So it's a length space. So we want to study length spaces. That's what we want to do. We don't want our metric space to be not length spaces. For example, metric spaces. Geodesic metric spaces are also length spaces. I will prove that. Yes. So an example is this one. Length spaces, not a geodesic metric space, is R2 minus the origin. Geodesic metric spaces are, of course, you know, a lot of examples. It's completely my own words. Yeah, so we want to study these objects rather than these. Now the question is, can I go from here to here? Can I define a new metric on X given a metric space which on the same set, which might change the topology, but has this property that's a length space? Can we go from a metric space to a length space? That is what we wanted. We wanted the induced metric from Rn, and we wanted the arc length distance rather. So, and yeah, we can do that. We can just define the left right hand side with a new distance function, and that actually defines a metric. Yes.